So in this video, we are going to be talking about sampling distributions. So let's start off with talking about sampling error. So sampling error is the natural discrepancy or error between a sample statistic and its corresponding population parameter. So basically what this is talking about is that every sample we take from a population is unique and different. And because of that, we would expect there to be some type of differences between the sample. So some differences in the mean, some differences in the standard deviation. You wouldn't expect that every single sample that you pull would match your population perfectly. That's just not reality. In addition to that, let's say I take two different samples from my population. I would also expect that there would be some differences between those two different samples. Again, because each sample is unique and different, a little bit different, you would expect there to be some differences in the mean, some differences in the standard deviation, things of that nature between two samples and also between the sample and its population. Now, because of that, we have some questions we kind of have to consider as we're talking about sampling and generalizing to populations. So the first thing we want to kind of talk about is how can we tell if a sample gives the best description of the population? So how do we know that if we pull a sample from a population, this is going to be an appropriate sample to use in order to run our treatment or things of that nature? And then of that, can we predict how the sample will describe the population? Are there things that we can do that will predict that this sample will describe our population in such a manner? And what's the probability of selecting a sample that has a very specific characteristic? Maybe you want to look at a sample and say that the mean is higher than this or the standard deviation is lower than that, things of that nature. And then the question that statistics really is trying to determine is if there is a significant difference from the population and the sample. So that's what we're trying to figure out. Is there enough difference that we could say that the sample and the population are different from each other? And that's really what we're trying to do when we're trying to do statistical studies. We take a sample, we do some type of treatment to it, and then we want to say, is the resulting measure different enough from the population to say that this treatment had a significant effect on this sample of people, so that we can turn around and say, we think that this treatment will have a significant effect on the population. Remember, that's what statistics is all about. That's what psychology is always about, trying to determine if there's differences between a sample and a population when a treatment has been applied. So now we're going to talk about the distribution of sample means. So every time we take a sample, we take a mean. So when we talk about sample means, that's what we're talking about. So if I take 20 samples from a population that have an N of a certain size, because we're always going to talk about the same N for every sample. So maybe my samples have 50 participants in them each. So I've got 20 different samples, each of them containing 50 people. What's the mean of each one of those 20 samples? That's our sample mean. So this is the collection of sample means for all the possible random samples of a particular size N that can be obtained from a population. Okay, so the sampling distribution is the distribution obtained by sampling all of those possible samples for a specific size. Now I've got a website here that you can kind of play around too, but we're going to play around with it here in just a second on looking at how those distributions happen. So let's go ahead and click on that. We're going to bring up this website. All I'm going to do is go ahead and say begin. And what we're going to have is right here we have a population, and it's a nice normal curved population. It's got a mean of 16, it's got a median of 16, it's got a standard deviation of 5. Okay, and what we're going to do is we're gonna do this data around our mean, and we're gonna bump our sample size. So our N that we're gonna do is we're gonna say we're gonna take samples of 20. So this is gonna be every sample of 20 people. Okay, so I want you to see what's gonna happen as we do this. We're just gonna do 5 to start with. So we're gonna do 5. So all of those boxes coming down are the sample the samples that we're doing. So that's 20 samples, and there's their mean. Okay, so we took 20 samples, there's the mean of those 20 samples. So now let's do 10,000. Now what I want you to notice here is look at the mean of these 10,000 different samples of 20 each, right? 15.99. Look at the mean of our original data, 16. Look at the median is 16. Look at the median of our data, which is 16. Now look at the standard deviation. That's a lot different than the standard deviation of this. And you can see it in the graph. Notice how this is a nice wide bell shape. Now this is still bell shaped. It's nice and uniform, but notice that the spread of that data is much more narrow. That's why my standard deviation is much smaller than it is here in my original data. So it's kind of a neat little thing that happens. As we do a sampling distribution, our standard deviation actually becomes much smaller because of the spread of those means is much more concentrated around the mean of the data. So now the other thing I want to show you too that is really kind of cool, we're going to clear this out and we're going to do a skewed graph. So this is our data, it's skewed over here, positively skewed or skewed to the right. Remember, when you do skewed to the right, that means the small tail is on the right hand side. And we're going to do the same thing. We're going to do our N of 20 and we're going to take just 10,000 really quick samples of 20 people in each sample. Okay, so again, I want you to look at this. My mean of all of my 10,000 samples is 8.09. Look at the mean of my original data, 8.8. Again, the median here is 8, a little bit off with 7, but that's okay. Notice my standard deviation again is much smaller than the 6.2 that it is right here. But look at the graph. Notice that my graph is no longer skewed. It's actually fairly uniform. Even though my original data was extremely skewed, my distribution of the means is going to be uniformed. It's actually going to be that nice kind of bell-shaped, but again, very, very little variation on it. My standard deviation is going to be very small because those means are all grouped around the mean of the original population data. Okay, so let's kind of go back and talk a little bit more about our sample means. So let's talk about some characteristics of the distribution of sample means. So number one, your sample mean should pile up around the mean of the population. We were seeing that in the thing where most of our data, we had a really small standard deviation because most of our data was right there around the mean of the original population data. The distribution of the sampling mean should be normal. Okay, again, seeing that nice bell-shaped symmetric curve shape, even though it was very condensed on itself, it was still nice and symmetric and normal. So we have a normal curve even off of skewed data. And here's the big kicker. The larger our N, so the larger our sample size, the closer the sample mean should be to the population means. Okay, so that means if I'm only looking at samples of N equal to 5, my data is going to be a little bit more spread out. I'm going to have a little bit more variation. But if I go up to sample sizes of N equal to 50, then my data is going to, my standard deviation or my variance is going to be much, much smaller. I'm still going to have the normal curve. We're just talking about how condensed that data is around the mean. If you guys have any questions, please let me know and we can go over any of these concepts again.